All right, so this example, actually, it's backwards, or it's going the other way. So we're not given a matrix. In fact, there's some space left for us to fill in the matrix, but let's figure out what we're supposed to fill in. So it's the 3 by 3 elementary matrix. Okay, well, that tells you what its dimensions are, but it's corresponding to the row operation. Take row 3 and replace it with 3 row 3. Okay, so that's the corresponding row operation. So, well, to figure out what to put here, you just say, okay, if you start with the 3 by 3 identity matrix and then perform this operation. So because I'm using a tablet here, it's easy for me to just write things down and then change it later. So let me start by just writing down the identity matrix. So that if I leave it like that, it's wrong, right? But what you have to do now is perform this row operation. So take row 3 and multiply it by 3. So what that would do is it would essentially change this 1 to a 3. And then, of course, the other two entries in that row are both 0. So that's the 3 by 3 elementary matrix that corresponds to this row operation. Okay, so here's 4 matrices, and we're not actually told which ones are elementary and which ones aren't. And actually, every example we've seen in this section, A, B, C, and D, were all elementary, but maybe not all of these ones are. Some of them might be elementary matrices, but some of them might not be. And we're asked to determine which ones are, and then for the ones that are, figure out what the corresponding row operation is. So this one, part A, is elementary. And the corresponding row operation, if I start with the 2 by 2 identity matrix and I take row 2 and replace it with row 2 minus 5 row 1, okay? Don't take my word for it. Just write it out. Pause the video and check. Write out the 2 by 2 the 2 by 2 identity matrix and then perform this operation on it. And you'll see that you get exactly this matrix. So because that's possible, then yes, it is an elementary matrix. This one, can you get this from the 3 by 3 identity with a single row operation? Yeah, just interchange the first 2 rows. Right, so this one is also elementary. And the corresponding row operation is to interchange rows 1 and row 2. By the way, I'm going to remind you of something. I've already mentioned this, but this is usually where there's always a few people that get a bit mixed up here. You'll notice that if I were to perform this row operation on this matrix, we would end up with the identity matrix. That is just a coincidence, right? That's not always going to happen. The way you should be thinking about this is not performing this operation on this matrix, but you perform this operation on the identity matrix. And as a result, you get this matrix. Now, for some matrices, it'll work both ways, right? In particular, for interchanging 2 rows. That's when it will work the same both ways. But that's not always going to be the case. Okay. What about this matrix? Is this an elementary matrix? Can you get this from the identity in a single row operation? And the answer is no. Not only can you not do it in a single row operation, you can't do it at all. And the hint here is that row of zeros. A matrix that has a row of zeros will never be row equivalent to the identity at all. There's never a way to carry it to the identity matrix. So the same thing works in the other direction. If you can't carry this matrix to the identity matrix, then you can't carry the identity matrix to this matrix. So if you can't do it at all, then you certainly can't do it with a single elementary row operation, which means this matrix is not elementary. So I'm going to say it's not elementary. And, well, if it's not elementary, then we don't need to write down a corresponding row operation because there isn't one. Okay, what about this matrix? We've got a 4 by 4 matrix. Is this an elementary matrix? Well, you could get this from the 4 by 4 identity matrix. In fact, here's how I could do it. Let's go back. Since we've got a copy of it up here, imagine I first added row 4 to row, ignore this. Now, actually, I'm going to, because I can put it back, I'm going to put it back in a moment, but I just want to erase it so that we can look at just this matrix. If I were to add row 4 to row 1, that would have the effect of putting a 1 here. So I'd have, the first row would become 1, 0, 0, 1. That's not quite the same as what I have here, but then I could multiply row 1 by 2, and then I would have my 2, 0, 0, 2 in the first row. So I could take this matrix, I could perform two elementary row operations and end up with this matrix. But that's not what an elementary matrix is. An elementary matrix is one that you can start with the identity and obtain that matrix in a single elementary row operation. So what I just described is not enough. So the question now becomes, what would we have to do to the 4x4 identity matrix to end up with this matrix in a single row operation? I'm going to move this stuff back again. And the answer is you can't do it. Try. I'd invite you to pause this video and try. Try every type of elementary row operation you can think of and see if you can somehow obtain this matrix from the 4x4 identity matrix, and you won't have to try very long before you're convinced that you can't do it. It's impossible. So this is not elementary either. Okay? So not every matrix is elementary matrix, but if they are, they're a square matrix that can be obtained from the identity matrix in a single elementary row operation. Okay, so now we're going to go through another bit of an exercise here. So what are we asked to do? Write down the 3x3 elementary matrix and E, giving it a name, call it E. Quite often that's what you do. Capital E is often used for elementary matrices. So write down the 3x3 elementary matrix that corresponds to this row operation, interchanging the first and third rows. So, well, if I start with the 3x3 identity matrix and I interchange the first and third row, what I'm going to end up with is this matrix. All right. So, okay, so that's part A. That's what the elementary matrix is, the 3x3 elementary matrix that corresponds to this row operation. Okay, in part B, what are we asked to do? We're asked to do something else with that same elementary row operation. We want to interchange rows 1 and 3. So row 1 and row 3, we want to interchange those. I'm just going to write it out like I usually do. So take row 1 and interchange it with row 3, and that will give us what? We'll have a 3x4 matrix, so 0, 0, 1, 0. That'll be the first row. 2, 0, 0, 2. That'll be the third row. So those have been interchanged, and then the second row is going to stay the same. Okay, so that is what we got for part B. Now, part C. This seems to kind of come out of nowhere, but what are we asked to do? We're asked to calculate a matrix product. So we want to multiply this matrix, E, by this matrix, A. Not this one, the original matrix A. Okay, well, let's do it. So E times A. So that's going to be this product of this 3x3 and this 3x4. Oops, I'm writing the wrong entries down, aren't I? I accidentally started writing this matrix. We want to multiply it by this matrix A. So the first row is 2, 0, 0, 2, 0, 1, 0, 0, and 0, 0, 1, 0. Okay, so, well, there's a lot of arithmetic involved here, isn't there? This is a 3x3, and this is a 3x4. So if you write out the dimension diagrams, the dimension diagram, the dimensions of the result is also going to be 3x4, and you have to work it out one entry at a time, as usual, right? So I'll start by doing a couple entries, and then I'll leave the rest to you as an exercise. So if I take this row and multiply it by this row, I'll get this entry in the first row, first column. So let's do that. 0, 0, 1, and 2, 0, 0. So I've got 0 times 2, 0 times 0, and 0 times 1. All of those are zeros, so they add up to 0. Let's do the next entry. So I'm going to have row 1 and column 2. So 0, 0, 1, and 0, 1, 0. So I just have 0 times 0, 0 times 1, and 1 times 0. Those all add up to 0 again. Okay, next element of this row. So 0, 0, 1, 0, 0, 1. So I've got 0 times 0, 0 times 0, and 1 times 1. So that's going to add up to 1. And 0, 0, 1, 2, 0, 0. So we got 0 times 2, 0 times 0, and 1 times 0. Those all add up to 0. Okay, carry on in this fashion. I'll do 2 more entries. How about, let's pick them at random. So I'll take this row times this column is going to give us this entry here, right? So I have 0, 1, 0, 0, 0, 1. You've got 0 times 0, 1 times 0, and 0 times 1. Those all add up to 0. So we'll get this. And I'll do one more entry. I'll pick it at random. What about row 3 times column 2? That'll give me the entry that's in row 3 and column 2 of the product. So 1, 0, 0, 0, 1, 0. You have 1 times 0, 0 times 1, and 0 times 0. Those all add up to 0. Okay? So keep going in this fashion. Fill in the rest of the entries. I'll leave it to you. But this is what you're going to get. You're going to get that for your second row, and you're going to get 2, 0, 0, 2 for the third row. And but I want to really, really emphasize something. Yeah, okay, some of you are probably already noticing, and this little hint here may have given the surprise away, especially once you're already partway done working through this. But when you work out this product, you're working out the product using the definition of matrix multiplication, right? It has nothing to do with part A or part B. It's only after you actually work out the matrix product that you see, hey, this is exactly the same as this matrix. Where did this matrix come from, the one I've got circled? How did this come to be? Well, we took the matrix A and we applied this elementary row operation. We interchanged the first and third row. So first and third rows. And how did this matrix come to be? Well, we took the elementary matrix that corresponds to this elementary row operation, and then we took our matrix A and we multiplied it on the left by this elementary matrix. And it is not a coincidence that we got the same thing in both cases. And that's what this next theorem is saying. Okay? This is the essence of why we care about elementary matrices. This is a really cool result. If you take any matrix A and you multiply it on the left, because remember, I have to say on the left, right? It's important that the elementary matrix is on the left here and that our matrix A was on the right. If I had flipped them, well, in this case, the dimensions wouldn't even work out. Product wouldn't be defined. But if I adjusted the dimensions so it was defined, we could not expect the same phenomenon to happen. But here's the phenomenon. If you take a matrix A and you multiply it on the left by an elementary matrix that corresponds to some particular row operation, that is the same as just applying the row operation directly, which is a really not obvious thing. And that's pretty surprising. But it's really cool. That's one of the really neat things about elementary matrices. The other really neat thing about them is they're essentially, it turns out they are the building blocks for any invertible matrix.